Hello everyone, and thanks for watching Edupedia World videos. Today we'll be learning about dimensional analysis. We saw in the last class that there are 7 fundamental units in the SI system and there are 2 supplementary units, and these can be used to form any units for any derived quantity which we want. All units can be described in terms of product of the powers of base quantities. For example, we know that speed is distance upon time. So the unit for speed is meters per second, which can also be written as per second can be written as second to the power minus 1. So speed is, there is no power of mass, the power of length is 1 and the power of time is minus 1 in speed. So we have decomposed speed into the base quantities. Out of all the 7 quantities, speed only uses 2 base quantities, which is length and time. The power of length is 1 and the power of time is minus 1. So the analysis of the units of derived quantities in terms of these base quantities, you can use another word, decomposition. The decomposition of derived units in terms of the base units is called dimensional analysis. For example, the dimensional formula of force is ml t to the power minus 2. Let me make that very clear. So we use slightly different symbols for dimensional analysis. So this looks like I'm saying speed equal to meters per second. That's not true because there is an arrow. So the way we write it as, we put a square bracket in between speed. Once we put speed in between square brackets, it means we're not talking about the physical quantity speed. We are talking about the dimension of the physical quantity speed. Dimension is just another word for units. But we don't write it as meter per second, we write it as LT minus 1. So the symbols these are the dimensional symbols. These are slightly different from the symbols for the units. For mass, we'll use M. For length, we'll use L. For time, we'll use T. And the rest we'll see as we go along. So the dimensional formula of speed is LT minus 1. Okay. We know what acceleration is. Acceleration is change in speed upon time. I'm just going to write speed for short now, but you know there is change in speed. So that means the units of acceleration are meter per second, which is the unit of speed, divided by second, which is meters per second square, which is meters and second to the power minus 2. So we would write it as the dimensional formula for acceleration is LT minus 2. So we've decomposed acceleration into the basic 7 fundamental quantities. The power of acceleration, or the terminology we use, is the dimension. The dimension of acceleration in mass is 0 because we don't see any m. The dimension of acceleration in length is 1. The dimension of acceleration in time is minus 2, and in all other quantities is 0. Right? So we could say in another way that the dimensional formula of acceleration is LT to the power minus 2. So this is what dimensional formula means, and we'll see that even without knowing the actual values, just by checking the dimensions, we can actually figure out a lot of things. So we'll deal with force in great detail in a few chapters. Right now all you need to know is that the definition of force, or the formula of force, is that it is mass multiplied by acceleration. This is Newton's famous second law. Force is mass times acceleration. So the unit is the unit of mass, which is kilograms, times the unit of acceleration. The unit of acceleration we saw here is meter per second square. So which is kilogram meter per second square. So we will say the dimensional formula for force is m L T minus 2. Let's just do one more quickly. We know that work is force times distance. I'm sure you've seen these definitions before, you've not really studied them in detail. We will do soon enough. So what is the dimensional formula of work? Try to guess before I write. You're right, the dimensional formula of work is mL2 T minus 2. Because mLT minus 2 is force multiplied by distance. Distance is simply L, length. So dimensional formula for work will be mLT minus 2. So with this way, if we know the formulas for certain quantities, if we know the formulas for an unknown quantity rather in terms of some known quantities, we can at least find the dimensional formula directly. Now, dimensional analysis has many uses. One of them is to check to see if an equation is correct. Another one which we'll see is to find formulas for unknown quantities. For example, if their dimensional formulas are known, this is a very useful property which has been used many times throughout history. And then you can convert units from one system to another. So for example, I could give you the force in CGS system of units and you wanted to find out the force in the SI system of units. So you could convert from one system to another using dimensional analysis. So let's see the first one to see if an equation is correct. This is decided by a very simple principle called the principle of homogeneity of dimensions, which says that we can only add or subtract physical quantities having the same dimensional formula. Right. So what this means is, I'm going to write down an equation which I'm sure you've seen before, which is V equal to U plus AT. Now in any equation, terms are separated by three symbols, either plus or minus or equal to. So in this case, we see there are three terms in this equation. One term is V, another term is U, another term is AT. We will treat AT as a single term. So terms are separated by plus, minus and equal to. And what is the principle of homogeneity of dimensions is, we can only add or subtract physical quantities having the same dimensional formula. What that means is, we can only add V to V. We can only add a speed to another speed. We cannot add a force to a speed. We cannot add a temperature to a time. 2 seconds plus 5 degrees centigrade does not make any sense. So we can see that we can always add or subtract same physical quantities. So if we are not adding or subtracting the same physical quantities, we can be sure that the equation is wrong. So we know that the dimensional formula for V is LT minus 1. The dimensional formula U is LT minus 1. V is the final velocity, U is the initial velocity, both of them are basically velocity. The dimensional formula of A is LT minus 2. The dimensional formula of T, time, is simply T. From that we see that the dimensional formula of AT is LT minus 2 times T, which is LT minus 1. So we see that the dimensional formula of V, U and AT are the same, which is LT minus 1 in all three. Let's look at another equation which you've seen. S is equal to UT plus half AT square, right? So the dimensional formula of S is simply length, it is L. The dimensional formula of UT is, you can calculate from here, U is LT minus 1 and T is T. The dimensional formula of UT is L. The dimensional formula of half AT square. What is this? We know that the dimensional formula of A is LT minus 2 and the dimensional formula of T is T. So the dimension of T square is capital T to the power of 2. What is the dimensional formula of half? The answer is nothing, because half is a constant. Constants do not have any dimension. Half is not measuring any physical quantity. So the dimensional formula of half AT square is the same as the dimensional formula of AT square, which is L. So we can see indeed that this equation is correct. Now let's see if somebody gave me an equation. V square is equal to U square plus 3AST. Let's consider this equation for a second. The dimensional formula of V square is equal to L to T minus 2, the square of LT minus 1. A dimensional formula of U square is equal to L to T minus 2. What is the dimensional formula for 3AST? The dimensional formula of 3 is nothing. For acceleration is LT to the power minus 2. Then we have multiplied by L. Then we have multiplied by T. So it is L2 T minus 1. So we see that the first term and the second term have the same dimensional formula, but the third term has a different dimensional formula. So we can see automatically that this equation is incorrect. There is no possible way this equation can ever be correct, because you cannot add a dimensional formula of L2T minus 1 to a dimensional formula of L2T minus 2. That violates the principle of homogeneity of dimensions. Okay, but we can see that if it were no T here, then this would be L2T minus 2. So we can see that V square is equal to U square plus 3AS is correct. It is not actually correct. It is dimensionally correct. However, is this equation actually correct? I'm sure many of you know that it's not. The actual equation is V square is equal to U square plus 2AS, and we'll see that in a few lectures. So the limitation of this method is we can definitely tell if an equation is incorrect. If an equation violates the principle of homogeneity of dimensions, it is 100% incorrect. But if it does satisfy the principle of homogeneity of dimensions, that means the dimensionally the equation is correct, as V square is equal to U square plus 3AS is. That does not mean the equation is actually correct. The equation might be wrong. We can be sure it is incorrect if it does not satisfy the principle. But if it does satisfy the principle, that is not enough to tell if it is correct. So that's a limitation of this method. Another use of dimensional analysis is finding formulas for unknown quantities if their dimensional formulas are known. This needs to be used in a certain special cases. One of them is we need to know the physical quantities on which the unknown quantity depends on. And we need to know that the formula is a product of the different quantities. So let's take an example. Let's say I'm trying to calculate the time period of a pendulum. For people who don't know what a pendulum is, it's simply a small mass attached by a thread, which is making an angle theta, and we let it go, and it just you've seen pendulum clocks, I'm sure, and it just moves back and forth. And we need to find the time after it repeats its motion. That means if I leave it from this position, it goes to this position and it comes back to this position. So how much time does that take? So let's say we know for a fact that the time depends on three quantities. We know that it depends on L, that is the length of the string. We know that it depends on M, which is the mass of the bob. And we know that it depends on G, which is the acceleration due to gravity. We know, for example, let's say we did the experiment on different places having different gravities, and we found out that the time period changed. So we know that it depends on these three, and we know for a fact that it does not depend on any other quantity, and we know that the dependence is of product type. That's a lot to guess, but many times it can be guessed. So we know that the time depends on the length, the mass, and the acceleration due to gravity, and we want to find out the formula. So what we do is we assume that the time is proportional to m to the power a, l to the power b, g to the power c. If the dependence indeed is of product type, then for different values of a, b, and c, we can satisfy this formula. For example, if let's say the time period would be Lm by g square, then a is 1, b is 1, and c is minus 2. But this is not actually correct, so let's forget this for now. So all we need to do is we need to find out the values of a, b, and c, and for that we can use dimensional analysis. Let's write the dimensions of all three here. The dimension of m is capital M, that's its mass. The dimension of L is L, that's it. the dimension of g is an acceleration due to gravity. We saw earlier the dimension of acceleration is lt to the power minus 2. What this means is that the dimension of t is the same as the dimension of m to the power a, l to the power b, g to the power c, which means it is capital M to the power a, that is the dimension of m to the power of a, capital L to the power of b, and lt minus 2 whole to the power of c. We can write this more neatly as m to the power of a, L to the power of b plus c, and t to the power of minus 2c. Right. But we also know that the dimensional formula for the time period is simply t. Right. So this has to be equal to t. If this is equal to t, then we get three equations for the three unknowns. We know that a has to be equal to 0, because if we say this is equal to t, what we are saying is this is equal to m to the power 0, L to the power 0, t to the power 1. So a is 0. We know that b plus c is 0 by equating the dimensions of L, and the dimension of t is minus 2c, which should be 1. So minus 2c is equal to 1, which gives us c is equal to minus 1 by 2, which gives us from the second equation b is equal to 1 by 2, and we know that a is equal to 0. So we've calculated the three values, and we can definitely say that the time period is proportional to m to the power of 0, L to the power of half, and c to the power of minus half. So that we can write it as root of L by g. And since it's proportional to root of L by g, we can write it as time period is k root of L by g, where k is some proportionality constant. So the limitation of this method obviously is we cannot find out the value of k from this method, but we still have found out a lot. For example, we really haven't done any actual analysis using Newton's laws. We really have not used any physics, but we can tell that if the length is increased by 4 times, L goes to 4L, then time goes to 2t. Length becomes 4 times, the root of 4 is 2, time becomes twice. So this is an amazing result which we've come up with, and you need to appreciate it. We did not know anything about how a pendulum works. All we knew is that the time period of a pendulum depends on the length, the mass, and the gravity. And we were able to say if the time period depends on the length, the mass, and the gravity, then when the length becomes 4 times its original length, the time period will become twice its original period, without doing any physics at all. So this is quite interesting. So the limitation of this method is we cannot find the proportionality constant by this method ever. Right? We need to find out from other ways, experiments maybe, what the proportionality constant is, but we can still find the relation, and that was pretty remarkable. The third use is converting units from one system to another. So we know that the joule is an SI unit of work, and we saw that the dimensional formula for work was mL2T minus 2. So 1 joule is 1 kilogram meter square per second square. And let's say I'm telling you that an erg is the CGS unit of work. So an erg will be equal to 1 gram centimeter square per second square. Somebody tells us that an object or a force or a person or a car did a work of 20 ergs. But we are more comfortable in our SI system, as we will mostly be. So we want to find out what 20 ergs is in terms of joules. So the first thing we need to do is we need to find out how many joules is equal to 1 erg. Right? So let's look at that now. We derived earlier that the dimensional formula for work is mL2T minus 2. Right? The force was mLT minus 2 multiplied by the distance. Right now all you need to know is what these things mean. You don't really need to know anything in detail. We'll study all of these things extensively soon enough. Right? So we want to find out 1 joule and 1 erg, the relation between them. So we know 1 joule is equal to 1 kilogram meter square per second square. That is 1 kilogram meter to the power 2 second to the power minus 2. Similarly, 1 erg is in the CGS system, so it has to be 1 gram centimeter square per second square. So what is 1 erg? This is straightforward mathematics. Divided by 1 joule, it is 1 gram by 1 kilogram multiplied by 1 centimeter by 1 meter whole squared multiplied by 1 second by 1 second whole to the power of minus 2. Right. Now 1 kilogram, remember the last slide of the previous lecture, kilo means 10 to the power minus 3. So 1 kilogram is 1000 gram. 1 meter is 100 centimeters. So that means 1 erg by 1 joule equals, here it's 1 by 1000 and here it's 1 by 100 whole square. These two cancel, they don't give us anything. So that is 1 by, this is 10 to the power 2 squared, so this is 10 to the power 4 and 10 to the power 3 becomes 10 to the power 7. So from this we know that 1 erg is equal to 10 to the power minus 7 joule, quite a small unit. From this we know that 20 ergs will be 20 into 10 to the power minus 7 joule, which is 2 into 10 to the power minus 6 joules, which is 2 microjoules. So we found out that 20 ergs is 2 into 10 to the power minus 6 joules, which is what we wanted. So this is the way you generally have to proceed when you have to calculate between different systems of units. So we found out that 1 erg is 10 to the power minus 7 joules, so 20 ergs is 2 microjoules. I can give you another example which is generally quite useful and you'll be using again and again, which is converting kilometers per hour to meters per second. So let's say we have x kilometers per hour. So x kilometers per hour will be, we want to calculate that in meters per second, which is by meters per second. So we know that 1 meter per second by 1 kilometer per hour is equal to 1 meter by 1 kilometer, 1 second by 1 hour to the power minus 1. Right. So from that we can see this is 1 by 1000 times, and hour is 3600 seconds, so this becomes 3600. That becomes 18 by 5, which means 1 kilometer per hour is 5 by 18 meters per second, which means that x kilometers per hour is equal to x into 5 by 18 meters per second, which is y meters per second. So for example, 80 kilometers per hour is equal to 80 into 5 by 18, you can simplify that to whatever it might be, 18 into 5 by 18 meters per second. So that's the end of this lecture. I hope the concepts have been clear to you. Thank you.